In this video, we're going to see how to optimize predictors in a regression simulation by using random feature elimination with cross-validation, or RFECV. So why RFECV? Well, what we do with this is we start with all features, and then we recursively, hence the R, recursive, recursively eliminate the least relevant features until the specified number of features is reached. So RFECV performs RFE, or recursive feature elimination, with cross-validation, which we'll talk about in just one moment. Once we've applied RFECV, we can take a look at the parameters that result and see which ones it thinks are the most useful to us. So first of all, what's cross-validation? We've seen train test split before, which is where we take our data and we divide it into a training subset and a testing subset. In cross-validation, we often use what's called k-cross-fold validation, where we partition the data into k equal subsets, whatever we set as k. Let's say we set it as 5. Then we train the model on k-1 subset, so 4 subsets in that case, and test on the remaining subset. And we repeat the process k times. So they're going to, k is 5, then we repeat it k 5 times. This helps to reduce the risk of overfitting. Now, one important thing to consider is when we're using our RFECV, we can give it a scoring model that tells us what's the most important way to look at the results and how do we know what's the best result. Well, the scoring options are important, as we'll see shortly. And we see it also depends on the type of model we're doing. So classification, we have accuracy, balanced accuracy, average precision, F1 weighted, lots of different things here. Clustering, several things we can look at for clustering. And finally, regression. We have max error, negative mean squared error, R2. So as we're walking through this, we'll play with a couple of these different values and see how it impacts our results. I start with our iris data set, and I've created this block here where we start by importing everything we're going to need, RFECV, logistic regression, because in this case we're looking for a categorical outcome, and then log loss. We start our logistic regression, we instantiate that and save it into the variable CLF, and then we instantiate our RFECV object, save that into RFECV variable. Estimator, what model are we using? Well, in this case, logistic regression. Scoring, max error. Remember that web page I just showed you? That's where we plug in the scoring result that we want. As I say, we'll finagle that a little bit and see what comes out of it. Then we do our fit, which is where we're training against the X training and the Y training. And next, we print out the optimal number of features, and we show the best features. And we can show all of that in a graph. So let's take a look at this setup with max error. And we see optimal number of features is 2. And the best features are X3 and X4. Not a big surprise because that's the same result that we got with our random forest classifier in a separate video. But nonetheless, you see it came up with 2 features, X3 and X4. And it shows us that, yeah, the right point is right there at about 2 features. Now, let's go ahead and change the scoring just a bit. We remember there are several different options we have for scoring. We have max error, we have R2, negative median absolute error. I'm just going to grab a couple of these and see how it impacts our model. So change from max error, and this one literally I just picked at random, negative median absolute error. Remember, with max error, we have 2 features, and it's X3, X4. Negative median absolute error gives us 1 feature, which is X4. Now let's try R squared, which is a common method that we use with regression. So R squared gives us 2 features, X3 and X4. And most of the other options will give us similar results. Let's try this on another data set as well. Going back to our election data, our multiple linear regression, and a couple things I need to do. First, When I did random forest selection in a previous video, I noticed there were a lot of columns that I needed to throw out. So in this case, I've decided to just go ahead and select a smaller set of possible features. Total population, age 29 and under, 65 and older, median household income, unemployment percent, less than high school percent, less than college percent, and rural percent. So I made a variable for that, and now I'm using that variable, which is a list, to say, okay, give me a smaller set, a smaller data frame. Now, those are the predictors. I also want to add the target, and remember, this is a classification result, so I'm adding the third-party county, just copying that over, and then that gives me the new data frame below with just those predictors and the third-party county. Now, I also need to scale the data, because take a look, population can be quite big compared to something like unemployment percent. They're on different scales. Less than college percent, rural percent. Okay, those are percentages, so the percentages are at least going to be 0 to 100. But then median household income, that's typically about 5 digits. So we see we need to do some scaling. So I'm going to import the standard scaler, not worried about scaling our target, just the feature column. So I'm going to drop the target while I do the scaling, and then apply the scaling. Now take a look at the results of the scaling. You notice we have an array, and we have an open square bracket, and somewhere down at the bottom a closed square bracket. Then within that we have a series of comma-separated square brackets. So this is effectively a list of lists. Now if we take a look at this list, we'll see numbers that are relatively small. Scalar is generally going to take each number and subtract the mean of the entire column from that number, and then divide by the standard deviation, so we get a nice tight fit with our numbers, and that effectively is giving it that scale. Think about that. Take value, subtract mean, divide by standard deviation. That's giving us a scaled number where it doesn't matter if it's population or zip code or income or anything like that. It's just saying, okay, the average of the set is now 0, and by dividing by the standard deviation, we're effectively getting a count of standard deviation, distance from the median is what we're getting. Now if you take a look at this, we have 1, 2, 3, 4, 5, 6, 7, 8 values. In each of these sets is going to be 8 values. Now we go back up to our list of predictor columns, and guess how many we had? 1, 2, 3, 4, 5, 6, 7, and 8. So while we don't have column titles and row indices as we normally do, you might look at this and say, what in the world is going on here? But just know that each of these matches up to a row from our data frame. And if you look at each item within that list individually, it matches up with the appropriate column from that data frame as well. But notice that the data that we have, you see E minus 1, E plus 0. The data that we have is now in a very tight range and has been scaled so that we can speak a common language. Finally, given that, I apply a very similar model that I just applied in our iris data set. I simply switch a couple things around, effectively using the new data frame that we've come up with and giving us a bit of output, and let's see what we get using R squared. Using R squared, it says to use all 8 features, and it shows us log loss versus number of features. Really, looking at this graph, I would probably ratchet it down to the 3 that are the most important, because it looks like we get a fairly good score with 3. Now, just out of curiosity, let's try this with max error again as our scoring technique. Here we see optimal number predictors is 1. So a very different result than we saw before. In describing what each of these possible scoring techniques does would end up making this a very, very long video, so I won't get into that here. But I will say, as you're evaluating models, it's worth looking at the differences between each of these scoring techniques. Let's take a look on our blueberry yield data now. So once again, I scale the results. I start with our standard scaler, and I use our smaller blueberry data frame And that's a data frame where I previously took out some columns that were not of interest. I transform everything but the target, and once again it gives me this multi-dimensional array where each of these elements effectively lines up to a row and column intersection in our data frame. Now we go ahead and do our train test split as we've done before. We drop out the target column and we say we want a test size of 30%. And now plug in that same RFECV as we've seen before. I just had to make a couple of changes here. I had to make sure that the variables that I used up above in train test split are the same variable names I used down below. And then when I'm printing out the best features, I take the smaller blueberry data frame, drop the yield column, and use the other columns as our index, and then print a little summary here. So let's try this with r squared. And we see that gives us 13 features, although here again I'd say once we get in the 8 to 10 range, we're probably at a fairly good point. Let's try it with max error. And max error again gives us 13 features, a little different look and feel on that. Negative mean squared error, again, that one also gives us 13 features. Now, I will say when I was rehearsing this, I was able to try a few combinations that gave a different number of features, but I suspect that's a matter of how the train test split happened to fall with our data. So, lesson learned is you might get slightly different results, and it's worth trying over a couple different ways, or at least using this as a starting point to decide which features you wish to use. So this has been a look at how to use recursive feature elimination with cross-validation. I hope you found this video helpful, and I look forward to reading your comments. Thank you.